Fortunately, every way we know to make a ketone and aldehyde, they're all review. So we're going to go through them very quickly. But if you recall, in the alcohols chapter, we learned how to oxidize alcohols, and we learned how to oxidize primary alcohols using PCC to make an aldehyde. And then we used either PCC or chromic acid for secondary alcohols to make ketones. And again, both those totally review. So again, primary alcohols to aldehydes with PCC, and then either chromic acid or PCC for secondary alcohols to ketones. We also learned ozonolysis for alkenes here, and does oxidative cleavage of the carbon-carbon double bond, and then both carbons in the alkene become carbonyls. Now, if we do this under reducing conditions, and that's all about what you use in the second step, and if you use dimethyl sulfide here, also abbreviated DMS, or zinc with water, either one of those will be the reducing conditions, and the big thing is that an aldehyde will stay an aldehyde. And again, if you'd done this under oxidizing conditions using like hydrogen peroxide, the aldehyde would have been oxidized to a carboxylic acid. But again, this chapter is all about making ketones and then aldehydes. And so that's why we're going to do this under reducing conditions. Now we also learned some ways to make ketones and aldehydes back in the alkynes chapter. Now, if you start with a terminal alkyne where the triple bond is at the end of the chain, so in both these first two cases, so you can make a methyl ketone if you use mercuric sulfate with sulfuric acid. That goes Markovnikov. If you recall, it actually initially forms an enol that tautomerizes to the ketone. And in this case, if you use a bulky borane and do hydroboration oxidation with your terminal alkyne, you get your aldehyde instead, and this goes anti-Markovnikov. So in this case, again, also forming an enol that tautomerizes to the aldehyde. Now, if you start with an internal alkyne instead, then it doesn't really matter which one you use. And it turns out with sulfuric acid, you don't actually need the mercury catalyst if you throw it in whatever. Or you can use the bulky borane. So in either case with the internal catalyst, works either way. And either carbon of the alkyne can be what eventually ends up as the ketone. So again, you're initially going to form enols with those tautomerized to give the keto form. So in this case, as long as your internal alkyne is not symmetrical, you actually get two different ketone products. But if it's symmetrical, you'd get just one ketone product. Then finally, in this last chapter on aromatic compounds, we learned how to do Friedelcrafts acylations. And in this case, if we use an acyl halide with aluminum chloride as our Lewis acid catalyst, we'll do an EAS reaction here, electrophilic aromatic substitution, with this Friedelcrafts acylation. In this case, we'll get a ketone. And there was a special variant of this called the Gattermann-Koch synthesis. And in this case, it turns out this lovely species, again, not stable enough to form, but carbon monoxide and hydrochloric acid react to form it. And then it's kind of from there, once it's formed, it's kind of just the regular Friedelcrafts acylation, but in this case, forming benzaldehyde. So ways we learned in the last chapter make both a ketone or an aldehyde on a benzene ring.